Hello, hello, physics. All right, this is our video over power, the last video for chapter 5 before we switch over to chapter 6. In this video, we're going to talk about power. I'm going to start by just giving you a rough definition of power. Officially, power is work done over time, or the work that is done divided by the time it takes to do it. So I use a funky looking P for power because there are so many P's in physics that this is easier than having, because we've got the pressure P, the momentum P, the period P. We've got a couple others that I'm not thinking of off the top of my head. So I use this thing for P for power. And that is defined as work over time. Now, with the work energy theorem, this can sometimes be energy over time. For example, you spend this much energy to do this much work. Therefore, work energy theorem says that the energy you have that has been consumed is equal to the work done. Therefore, we can take the energy over the time instead of the work over the time, which is the same thing because the energy is equal to the work. And then that's going to obviously give us our power. Energy and work obviously are both measured in joules. And time is measured in seconds. Power, a joule per second, is measured in watts. And that is why I wrote out work instead of using a W. So watts, W-A-T-T-S, are the units of power. So whenever we're talking about power, we're talking about work that was done over how much time it took. That's pretty much it. I do want to throw something out there. Keep this in mind, something for you to think about, maybe ask about in class. We'll see how many people actually watch the video before the quiz. If power is work over time, but we are charged by the kilowatt hour, then what are we actually being charged for our use of? Are we being charged for our use of power or something else? Hint, I wouldn't have asked if it was power. Now, I'm going to go ahead and do a practice problem with you guys. It's pretty simple. Power is pretty straightforward. We don't, even in the college class, they don't spend a whole lot of time on it. I'm going to do problem, I want to say 50. Yes, 50 out of the textbook. It is on page 157 if you want to pull that up. All right, skier of mass 70 kilograms is pulled up a slope by a motor-driven cable. How much work is required to pull him 60 meters up a 30-meter slope, assumed frictionless, at a constant speed of 2 meters per second? What power must a motor have to perform this task? All right, so we're given a few things here. We start with this dude, and I'm just going to draw a dude hanging onto a string. And it's carrying him 30 meters, 60 meters up a 30-degree slope. And it tells us that his mass is, I can't hold anything in my brain today. It's 70 kilograms. It tells us the length of the slope and the angle, obviously. And it tells us that he has a constant velocity of 2.0 meters per second. How much work is required? Okay, this is not a work energy theorem problem. This is just a work problem. We are raising him by some distance s, and we are resisting the force Fg. Okay, so we need to use trig to get the distance s that he's being raised, take that s times the force of gravity that we are fighting to raise him, and that will give us our information. Since he's traveling at a constant speed, that means that we can say that Fg is equal to the force being applied. If he was not moving at a constant speed, then we would have to do a sum of forces diagram and figure out what the applied force was, because he'd be accelerating as he goes up. But as long as he's traveling at a constant speed, we can say that they're the same, that the applied force has to be equal to g. So in other words, if this is our dude, if we're applying a force to raise him against the force of gravity, if v is constant, then a is 0. And if a is 0, then Fa equals Fg. If a is not 0, then Fa minus Fg equals Ma, which makes our equation slightly more complicated, because Fa has to be larger than Fg in order for this to be true. But, thankfully, we don't have to worry about that, because it is the case. So, we can say that our applied force is equal to his mass times the acceleration of gravity. We just need to find s. S is opposite, so we take 30, or we're going to use cosine because we're opposite, so 60 cosine theta will give us s. And then s times f, which is going to be m times g, will give us our work. So F, the applied force, is going to be equal to his mass times the acceleration of gravity. So if the work is Fs, then I'm getting smaller and smaller. Can you still see that? Yeah, okay. So then the work has to be equal to his mass times the acceleration of gravity times 60 times the cosine of 30. And yeah, that's still on the screen. Okay. So if we plug that into a calculator, which of course is not at my workstation. So his mass is 70 times 9.81 times 60 times the sine, times the cosine of 30. That gives us that the work done to raise this man, however far that is going to be 35,682 joules. Now, sig figs requires us to round this to 36,000 joules with the 6 underlined, because we have 2 sig figs in all our numbers, so we can only have 2 sig figs in that answer. So that is A, and we haven't even done the power yet. The power is actually easier, because it says what power must a motor have to perform this task. So right off the bat, we're going to notice that we don't have time. Power is work over time. We have work, but we don't have time. But we do have velocity. We have a constant velocity, but it's a velocity moving at an angle. So we're going to have to break it into components. So we'll have to do this again, but with the velocity in order to actually find his speed that he's moving up with. Once we have the speed and the distance, we can determine the time because S is equal to Vt when A is 0. So I'm going to pause this, erase some stuff so that I've got room to write things out so you can actually follow along a little better with what I'm saying. Okay, so I've redrawn our diagram over there a little bit. So we have same thing, 60 meter slope, traveling at 2 meters per second at an incline of 30 degrees. We know that S is 60 cosine 30, and yes, you could put a number here. I just like to eliminate rounding whenever I can. And what I was saying with S and B, our third kinematic equation tells us that S is equal to VIT plus AT squared over 2. But since A is 0, the second half goes away, and so S is equal to VIT. So we know S already. We can use this to get V. Wow, that's kind of hard to see. I'm just looking at that. Hang on. I'm going to redo that in a different color. Okay, I've tried a couple of things, and it looks like my camera just won't focus in this section up here. I think it's because there's a lot of erasure residue up here, and it's making it, there's so many different things that's making camera have trouble focusing. So I'm going to do most of my work down here, below this point, where it should be able to focus easier because I'm erasing this section constantly. So I apologize for that. But this diagram is exactly the same as this diagram, except it has 2 meters per second in addition to the 60 meters. So, S is equal to VIT, or in this case, VT, since I is V, it's not changing. So then, we just need to find V. Well, we know that V or Vy is going to have to be the same here, except using our 2 instead of our 60. So we want the y component because we want the vertical displacement because our horizontal doesn't matter in terms of work. So we only want the vertical. So Vy is going to be equal to 2.0 times the cosine of 30. And then we can plug this into this equation. And if we do a little algebra, we get that t is equal to s over Vy. So t is going to be equal to 60 times the cosine of 30 divided by 2.0 times the cosine of 30. And we see something really cool here. Since the cosine of 30 is in the numerator and the denominator, it actually divides out. And we just take 60 divided by 2 and get that t is going to be 30 seconds. Then we just take our 30 seconds, plug it into our power equation. And so our work done was 36,000 joules. So 36,000 divided by the time it takes, 30 seconds. And that's going to give us our power. I'm not going to do that in my head. Hang on. Okay, so 3,600 divided by 3, 1,200. Duh. Okay. So our power is going to be 1,200 watts. Now, most of your power problems are not going to be this complicated. You're not going to have to do this stuff with them. But again, if we have any trouble, or at least nothing I'm going to give you, I'm pretty sure that the power problems in your homework are easier than this one. But that's it for this video. I'm going to go ahead and wrap it up because I don't want it to go too long so it doesn't take forever to upload. And I'll see y'all in class. Have a wonderful day.